We've had occasion to deal with several different types of quantities that start with the letter E. I'll remind you that these quantities all have the unfortunate similarity that the symbol E is used for all of them. We've tried to stylize the E in different ways to mean different things in different contexts. But let's remind ourselves of what these E's are. We have E for energy, and we've tried to make this a Roman style capital E, such as kinetic energy or gravitational potential energy. We've dealt with an E for electric field. So when there is charge that's in the presence of this electric field, then the charge would feel some force. There's been this script E that stands for electromotive force, something that gives charge energy in a circuit, something that pushes the charge around, such as a battery or a generator. There's a lowercase e that stands for the elementary charge, the charge that's on the electron, the charge that's on a proton. The sign tells us which kind of charge we're talking about. As you work these different problems, keep these different E's straight. Hopefully you'll find that the context will make clear which one it is that you're using. In this lesson, we want to focus our attention on electromotive force. This is the script E that we've been stylizing here to represent how much electrical pressure that a source exerts on charges moving in a circuit. Let's imagine that I have myself a D-cell battery. You can imagine your favorite brand battery here. It has a knob on one end, which represents the positive terminal of the battery, and it has a flat side, which is the negative terminal of the battery. So in an electrical circuit, when we draw it, we would put the negative side, the small line, and the positive side would be the large line. The circuit symbol would look something like that. And so far, we have said that these terminals are giving the same ideal voltage that the source of EMF provides. In other words, we have not distinguished between the EMF that the chemicals in the battery are able to provide and the terminal voltage, which we call V. Your textbook calls VAB. The difference in potential between terminal A, which is usually taken to be the positive terminal, and terminal B, which is the negative terminal. And if you have an ideal source of EMF, in other words, one that has no internal resistance in it, then these two things, the EMF and the terminal voltage, are the same number. I would venture to guess that more than 90% of the kinds of problems you're going to solve for the AP preparation and the AP exam are going to have ideal sources of EMF. But then there is that 10% that's left over, and that's what we want to concern ourselves with now. What happens when there is internal resistance in our source of EMF? How do we handle that? We might begin by asking ourselves, what do we mean by internal resistance? And what we mean by internal resistance is anything that's going to lead to a drop in the amount of energy that a source of EMF is able to provide for the charge before the charge actually reaches the terminals of the source. In terms of this D-cell battery right here, as the chemicals react inside the battery, there is a little bit of heat that's generated, and it turns out that that heat robs the charge of some of the energy it might have otherwise received before it actually makes its way into the circuit. Usually when we say a battery has gone dead, quote unquote, what's happened is not that the chemicals have been exhausted, but that for whatever reason the amount of internal resistance in the battery has increased so much that the energy that the source of EMF provides to the charge is insufficient to do whatever job it needs to do, such as light a light bulb when it's in a flashlight. Schematically in a circuit, the way we're going to indicate internal resistance is with a little box around a resistor and a source of EMF, and that box indicates our battery that has a negative terminal and a positive terminal. We'll call the higher potential end A and the lower potential end B. The source of EMF inside, say the chemicals in the battery, or if I have a generator, maybe it's the coil of the winding that's in the generator, has an ideal amount of energy it can provide, electrical pressure, that we'll call script E for the EMF, and then this little squiggly line inside is going to be the internal resistance. So now if I place this actual source of EMF in an electric circuit, then what ends up happening is the rest of the circuit doesn't see the full electrical pressure that the battery is providing. What it sees is only what comes out of the terminals A and B. So I could sketch a circuit that looks something like this. The resistor big R here doesn't see the full EMF, it just sees the terminal voltage VAB. If we want to compute what the actual terminal voltage is, we'll find that the more demand that there's placed on the circuit for current, then the lower this terminal voltage is going to be. And we'll compute that by saying that the terminal voltage VAB is equal to the EMF minus the current times the internal resistance. And that's going to be the formula that we'll use to figure out what the terminal voltage is. That terminal voltage is going to depend on the demand that's made for the current. So the higher the current is, then the lower the terminal voltage is going to be. Sometimes trying to figure out what this terminal voltage is going to be a primary question that's in the problem. Sometimes it may just be an offshoot of something that you'll need to actually handle. Here's an example problem that we can solve. A 9-volt cell with an internal resistance of 0.9 ohms is connected to an 81 ohm resistor. Determine A, the terminal voltage VAB, and B, the power dissipated by the resistor. Okay, so now how am I going to figure this out? Well, I need to figure out how much current that there is in the circuit. So the first step in solving problems like this is to redraw the circuit and break the little internal resistor out of the battery temporarily so that you can figure out what the current would be in the case of you having an ideal circuit. So redraw your circuit to look like this. Now what I've got is what looks like a circuit that has two resistors in it with an ideal source of EMF. This ideal source of EMF is still the same numerical value that it was before I broke the little resistor out. And now what I want to do is I want to combine these two resistors into a single series resistor and figure out what the current is through that single series resistor. Now let me actually figure out what the current's going to be in this circuit based on this situation here. And I'll say that I is going to be equal to E divided by RS, where RS is the combined resistance of the external resistance, in this case the 81 ohms, and the internal resistance, which is the 0.9 ohms. And now I'll put my numbers in and just solve this problem for the current. 9 volts divided by 81.9 ohms. And now I need my calculator. I get 0.1099 amperes. Nearly 110 milliamps is what I've got here, and I realize that I've got more significant figures than I really need. Well, now what? What I do with that is I put the fact that this is going to be the current in this circuit back into the original circuit and realize that I'm not going to see the external resistance R isn't going to see the full 9 volts. It's going to see something a little less than the 9 volts. The terminal voltage that it's going to see is going to be given by E minus I times the internal resistance. So this is going to be the 9 volts minus this 0.1099 amperes. I'm going to keep all of the numbers that my TI-89 calculator gives me, times the 0.90 ohms, that's the internal resistance. So what the battery actually sees is going to be computed that way. What the external resistance actually sees is 8.9 volts. It doesn't see all 9 volts. So how much power is dissipated by the resistor. Now, by the resistor in this case, what they mean is the external resistance, the 81 ohms. There are a couple of ways I could solve this. I could either say that the power is going to be I squared R, so you have power dissipated by the resistor is going to be I squared times that resistor. Or another way that you could do it is to say that the power is equal to V squared over R, where V squared is going to be the VAB that the resistor actually sees. And you could compute it that way. You could not say it's going to be E squared over R because, again, the resistor, the external resistor, doesn't see the full power of the EMF. So let's compute and see what it is that this external resistor dissipates. I'm going to do it both ways. Let's start with the first formula. P is going to be I squared, that's the 0.1099 amperes squared, times the 81 ohms, and now you put that into your calculator. And I compute 0.978 watts is what this resistor gets. On the other hand, if I used the other power formula, then I would say that the power is going to be V squared, this 8.901 volts, because that's what's actually falling across that resistor, divided by R, which is 81 ohms. And again, now I need my calculator. Numerically, I get the same answer as I did with the I squared R formula. What you could not do is to say that the power that is dissipated in the resistor is equal to E squared over R. That's not right because that EMF is not seen completely by the resistor. Hopefully you will not get problems that have internal resistance on the AP exam. You will get problems like this in problem sets and on tests, and I hope that you don't get them in a network of resistors, but it's possible that you might. So you need to know how to do it. So for now, that's it.